Okay, welcome back to calculus. We're going to continue our work in chapter 10 here, looking at parametric functions. In section 10.1, we were looking at sort of how to graph a curve that was given parametrically, determine its direction. We also looked at the problem of how to parametrize a given curve, like a line segment or an arc of a circle or a graph of a function. So in section 10.2, we're going to start turning our attention towards calculus questions on curves that are given parametrically. So in particular, if I'm given some parametric curve, that is, I'm given two functions, x of t and y of t, maybe like the picture that's drawn there, that might be its graph in the xy plane. So if I pick some point on that graph, x of t, y of t, I've shown you one. The calculus question I want to talk about in this lecture is, well, how would I find the slope of the tangent line at that point, right? Typically, to find slopes, you take derivatives. But to take derivatives, I would need to have y as a function of x or x as a function of y. This curve is neither. This curve loops around on itself, so it doesn't define y as a function of x, and it also doesn't define x as a function of y. So I need some other technique. But the idea that we're going to focus on is, okay, the whole curve doesn't define y as a function of x, but it does locally. So let me explain what I mean by that. I'm going to say that locally, in a small neighborhood around that point, I can think that y is some function of x. I'm just going to call the function f of x. I don't have a formula for it, and I don't need one. So, but locally, y is some function of x. Let me try to explain a little bit what I mean by that. Locally, I mean, once I pick this point, if I focus my attention on a small section of the curve around that point, I'm going to kind of erase part of this thing just temporarily to help you focus your attention. So remember, this thing is not a function of x globally because the curve doesn't satisfy that vertical line test, right? But if I only look at that red part of the curve, if I temporarily ignore the rest of it, that little red arc does satisfy the vertical line test. Well, that's what I mean by locally y is some function of x. If I stay in some small neighborhood of that point, then the y values are some function of the x values. Okay, so I'm going to take advantage of that. Again, I don't need to know the formula, but I know for any t, y of t would have to be the output value, the point on that graph that I get if I plug x of t into this function. Okay, and I can differentiate both sides of that equation with respect to t. I can take the derivative of y with respect to t, assuming it's a differentiable function. And I can take the derivative of the right-hand side with respect to t. I just need to use the chain rule. Okay, so the right-hand side's derivative would be f prime of x of t, but I need to multiply by x prime of t. So I differentiate that right-hand side with the chain rule. This probably reminds you a little bit about implicit differentiation. In fact, it's the same kind of idea. Okay, so I want to know the slope. Well, the slope is the derivative f prime of x. So I want to solve this equation for that term that I just underlined in blue there. So f prime of x, or I can write x of t. I'm typically going to write this in the Leibniz notation, dy dx. In either notation, I mean the slope. I mean the slope of that line that's written above there. And if I do the algebra above, what do I get? I get that that's y prime of t divided by x prime of t. Okay, so that's kind of the fundamental result of the lecture. We've got it kind of right away. The main result is that if you're given a curve parametrically by two functions called x of t and y of t, and you pick some parameter values, so you're picking some point on the curve, how do you find the slope of the tangent line at that point on the curve? Well, you look at the derivative y prime of t divided by the derivative of x prime of t. So this is kind of a nice formula to remember because in some sense it says what we kind of expect. Slope is the change in y over the change in x, right? That's a very familiar expression to anybody who's had analytic geometry courses. Slope is change in y over change in x. It's just here by change in, we mean derivative with respect to the parameter value. Cool. So that's kind of our main result of the lecture. That's how you compute the slope of the line that's tangent to a point, x of t, y of t, on a parametrically defined curve. Let's look at a concrete example. I'll leave that formula where we can see it. Here I've got some example drawn. This has a small typo in it. I didn't mean that square there. So let's take our function to be x equals t squared and y equals t cubed minus 3t. Okay, that defines some parametric curve. T can be any real number. T can be any real number. And I want to find the slope. I want to find dy dx. So I'm just mechanically using that main result that's written right above here. If I want to find that slope, what do? I have to take the derivative of y with respect to t. So that's the derivative of t cubed minus 3t. So that's going to be 3t squared minus 3. And I'm going to divide that by the derivative of x with respect to t. That's 2t. Okay, so you just take y prime and x prime separately and divide them. That's the derivative at any point t. Notice that the answer here is in terms of t. So you have to get used to that. You might be used to like the answer to the question like what's dy dx being in terms of x or maybe in terms of y and x. But here everything's driven by the parameter. So the x coordinates in terms of t, the y coordinates in terms of t, the derivatives are in terms of t. Everything is driven by the parameter. Once you specify a parameter value, then you have a specific place on the curve. Like for example, let's continue this a little bit here. If I choose some parameter value, I'm just going to randomly pick one that's convenient, like let t equal 1. Okay, well then my point, x of t, y of t, the parametric equations tell me what the coordinates of that point are. If t is 1, then t squared is 1. T cubed minus 3t is going to compute out to be negative 2. So when the parameter value is 1, then the point on the curve is 1 comma negative 2. Any parameter value determines a point on the curve in the same way. What's the slope there? Just going to use the phrase at t equals 1. I could also say the slope at 1 comma minus 2. It's the same information. Well, the slope there is the derivative. So I'm still plugging t equal 1 into something. It's just that I'm plugging into the derivative. I'm not plugging into the x and y coordinates separately. Well, 3 times 1 minus 3 is 0 over 2 times 1 is 2. So that slope is 0. Okay? So what does that mean? That means at the point 1 comma minus 2, i.e. when t is equal to 1, the tangent line is horizontal. All right, so I know something about this curve. I didn't have to have a picture to look at it, but I do want to look at a picture. So here, I'm going to split the screen real quick. Let me bring up my Desmos window. This will take just a second and kind of slide that over so it doesn't take up quite so much room. Here I've got this thing graphed in Desmos. I just put in the parametric equations, t squared and comma t cubed minus 3t. And, like usual, I've got a slider here. I can look and see what direction the curve is sliding. So if I change the value of my parameter down here, I can see that the curve is swept out in the way that point is moving. And if I bring that parameter value to where it equals 1, so I'm almost there. We just passed 0, and now a is climbing up, 0.6, and so on. Try to stop right on 1. Oh, mouse moved. There you go. So you can see in the upper right-hand corner there that point is at the point, well, we know its coordinates. We know the coordinates of that point are 1 comma minus 2. I think you can kind of see that in the graph scale as well. And the tangent line there, sure enough, it looks horizontal. I'm going to scroll down here a little bit. I've got that picture sort of where I can draw on it statically. So moving that parameter, we just convinced ourselves that this curve is swept out like that as t goes from minus infinity to infinity. And when you're at t equals 1, excuse me, when you're at t equals 1, you're at that point 1 comma minus 2, and we have a horizontal tangent line there. Okay? So I'm going to ask some questions. I could pick other t values and look at slopes of tangent lines, but here I'm going to ask a question. Are there any other horizontal tangent lines? So are there other horizontal tangent lines? I mean, you can see another one in the picture. It looks like there's one right there. Yeah. But we're only looking at a finite piece of this picture. So for all I know, oh, I'm going to move that thing. Maybe this curve has some behavior that we're not seeing in this particular picture. You know what I mean? Like maybe, for example, this curve, if we looked at bigger and bigger values of t, maybe out here it bends down somewhere. I don't know. If it did, it would have some other horizontal tangent line. So how are we going to answer that question? Well, we're going to answer that question in the following way. These slopes, you can still see the main result at the top of the screen there, y prime over x prime. Well, a tangent line is horizontal. Let's think about when that could possibly be true. When could a tangent line be horizontal? Well, it's horizontal when the slope is 0. So dy dx, which is y prime of t over x prime of t, has to be 0. Well, that's going to be true if and only if y prime of t is equal to 0, but x prime of t is not. So the denominator is not 0, so the fraction is defined, but the numerator is 0. All right, so that's what makes the slope 0. So in our particular example here, our y prime of t, well, it's 3t squared minus 3, which is certainly equal to 3 times t minus 1 times t plus 1. And so that's going to be equal to 0 for two values of t equals 1 and t equals minus 1. I'll leave it to you to check with these equations over here that when t is equal to minus 1, you're at this point. Let me just zoom in so I can write it a little nicer. You'd be at the point 1 comma 2. So now we know that that curve doesn't bend around on itself like I was hypothetically speculating. There's two tangent lines that are horizontal. And I'd like you to please kind of keep this in mind because I'm going to ask you questions about horizontal and vertical or horizontal tangent lines all the time. Tangent lines are horizontal when y prime is 0, but x prime is not. Okay, so this curve has two of them. Nice. What about vertical tangent lines? Vertical tangent lines. We can see one in the picture. It looks like it's right there. And the y-axis itself is the vertical line that's tangent to the curve. And again, you could ask the question, well, are there others maybe that we can't see? So in the same way, vertical tangent lines, well, if you're looking at this slope expression up here, a line is vertical when its slope isn't defined. So that means the denominator of this expression is 0, but the numerator isn't. So this is kind of another fact I want you to have in your pocket, that if you have a vertical tangent line, if and only if y prime of t is not 0, but x prime of t is. All right, so in our particular example, x prime of t is 2t. So 2t is 0 if and only if t is 0. You can check in the differential equations that puts you at the origin. So if I kind of zoom in here for a second just to write it nicer, when t is 0, we're at the point 0, 0. We've got a vertical tangent line there because our slope is undefined, and there are no others. There are no other vertical tangent lines. Nice. Okay, so continuing along here, I'm just kind of illustrating lots of stuff. We're going to do some more mechanical examples computing these derivatives, but these are typical questions that I'll ask you about curves. Where are the tangent lines horizontal? Where are the tangent lines vertical? Okay, so you know how to check those things. It's you look at the numerator and denominator of the derivative fraction, and you find places where one of them is 0 and the other one isn't. Okay, if they're both equal to 0, you might have a horizontal or vertical tangent line there. You'd have to check that out like it's an indeterminate form. So you might have to use some techniques like L'Hopital's rule or something like that. Okay, so actually, I mean, having said that, I should put some quotation marks around this if and only if, because it's possible that you could have a horizontal or vertical tangent line at a point where both x prime and y prime were 0. Right. So the really maybe to make this video factually correct, I shouldn't say that those things are if and only if, but I can say that If y prime is 0 and x prime isn't, then you have a horizontal tangent line. If y prime isn't 0 and x prime is, then you have a vertical tangent line. And in the case that it's not an indeterminate form, those things would be if and only if. Okay, a little complicated. All right, so here, I want to continue to ask questions about this thing. I'm going to pick this point on the graph right here. If I zoom in on it, you could trust from the scale, but let's just say I happen to know that that's the point 3, 0. And I can see that there's kind of two tangent lines there. Yeah, there's two tangent lines at 3, 0. One of them, I'll just draw a little piece of it, looks like it has a positive slope. And another one looks like it has a negative slope. So I want to kind of investigate what is going on at that point. How can there be two tangent lines? Well, we have to kind of figure out, well, what's the value of the parameter that puts us at that point? So we have to answer the question, what value of t, or what values of t, make x equal to 3 and simultaneously y is equal to 0? Okay, well, our parametric equations, we just have to solve a couple of things for t. So I have to set, well, I want t squared to be 3, and I want t cubed minus 3t, which is certainly equal to t times the quantity t minus root 3 times t plus root 3. I want that to equal 0. Well, the first equation has two solutions. T is equal to plus or minus the square root of 3. The second equation has three solutions. T is equal to 0 and plus or minus the square root of 3. But I need both of these things. I need both of these equations to be true at the same time. So I'm going to rule out t equals 0. T equals 0 makes y equals 0, but it doesn't make x equal to 3. We already saw that in our graph up here. When t is 0, we're at the point 0, 0. So there's two t values there, right? And we already know by the direction of the curve, let's not forget that negative the square root of 3 would come before square root of 3. So if you watch the animation over here, if I kind of pull this point back a little bit, the first time we pass through that point, t is equal to the square root of 3. Desmos is approximating that as about minus 1.74. And then as t continues to increase, we'll pass through that point the second time, and it's equal to positive the square root of 3. Okay, I kind of didn't leave the cursor there, but when we get to that point right there, for the second time, 1.75 is approximately equal to the square root of 3, the positive square root of 3. Cool. So those are the two values there. So let's find the slopes. Let's just do the positive one. So what is the slope? Oops, wrong color. What is the slope when t is equal to positive square root of 3? Well, it's off the screen here. Remember our slope up at the top? Let me just scroll back here. I'm just going to plug in on the fly, but you can stop the video and kind of write this down if you haven't already written it down. The slope is 3t squared minus 3 over 2t. So if I plug in square root of 3 into that, well, 3 times t squared is 3 times 3 minus 3 over 2 times t. So that's 2 times the square root of 3. Okay, and you can stop the video. I'll just simplify this quickly so the video is not too long. That's going to simplify to be the square root of 3. Okay, so this one tangent line here with positive slope, I'm just going to kind of make it longer so we can see it a little bit better. Make sure you understand why I'm picking on this one, because I wanted the positive slope one, the one when t is positive square root of 3. Well, its slope there is also the square root of 3. There's a lot of 3's in this problem. It's kind of the symmetry of this curve. All right. So I said up at the beginning I was going to remind you of how to find the equation of the tangent line. Well, you know how to find the equation of a line once you know a point and a slope on it, and we know both, right? We know the point is 3, 0. We just determined that the tangent slope was the square root of 3. So if you want to write the equation of the tangent line, you just use the point slope form. All right, so you can simplify that if you want to. It's just the square root of 3 times x minus 3 times the square root of 3. That's the equation of the tangent line over there. I've got that thing kind of ready to go here in Desmos. I can turn it on. You can check out that that purple line, whose equation is square root of 3 times the quantity x minus 3, looks perfectly tangent at that point. Nice. In fact, before we leave this example, I'll show you that what I programmed into Desmos down here is I've put in the tangent line at a point where t is my variable. So maybe if you can see in this formula 4 there, I just put in my 3t squared minus 3 over 2t, but I'm calling t equal to a, and I'm just writing the point slope form of the line. So that green thing in there, that tangent line, will move with my point. So that derivative is exactly what we've captured here. There's one of the values, t equals minus 1, where the tangent slope was 0. And then the tangent slope is undefined when t is 0. Then it was horizontal again when t was equal to 1. So I've got the tangent slope at every point on that curve. Okay, so that green tangent line kind of moves with the point as I move along the curve. Super cool. Okay, so this video is getting a little long. Let's do a couple of just sort of mechanical examples. I've got a second example here. If you watched my video on the cycloid, you recognize these parametric equations. Okay, these are the parametric equations of the cycloid, or the path that a point follows, that if it is on a wheel that's rolling without slipping. So I've got a little animation of what this curve looks like over there, and we can see its direction. But I won't make this a super long example. I just want to practice finding the derivative. So let's find the slope, dy dx. So the main result of the lecture says, well, you take y prime, that is 1 minus cosine t. We'll differentiate it with respect to t. We divide it by x prime. Okay, so you have to be able to differentiate these functions, and you need to put them in the correct order. Okay, so I'll leave it to you to check the details, but the derivative of 1 minus cosine t, when it's all said and done, is going to simplify to sine t. And the derivative of 1 minus sine t is going to be 1 take away cosine of t. So there's my slope, and as advertised, it's in terms of t. It always will be. And I'm not going to do it here in this video, but I hope you'll stop the video, and you got to watch when I highlight these things. I hope you'll ask yourself, where are the tangent lines horizontal? You can see over there in the picture that they'll be horizontal every so often. It's a periodic function. Where are the tangent lines vertical? Are there values of t that make the cosine t equal to 1, but sine of t, so the denominator is 0, but the sine of t isn't 0? Okay, so you can check out those values. Cool. Maybe this is going to have an indeterminate form. Like what is a value of t that makes the cosine of t equal to 1? Well, like 2 pi, for example, you can see it in the picture there. Cosine of 2 pi is 1, but the sine of 2 pi is 0. So in order to find, in the picture, it looks vertical, but if you want to find dy dx when t is equal to 2 pi, you're going to have to use L'Hopital's rule. Right? Because when you plug in 2 pi, well, the sine of 2 pi is 0, but 1 minus the cosine of 2 pi is also 0. All right, so that's an indeterminate form. 0 over 0 is an indeterminate form. So you're going to have to check out the value of that derivative with limits. It looks to me from the picture like the tangent line goes vertical there, but maybe that's something you can investigate. Okay, one more just quick mechanical example. Here I've got a couple of functions. I wanted to include some exponentials and algebraic functions. So if somebody asked me, hey, if this curve is given parametrically, I don't even have a graph of it ready. But if they wanted me to find its derivative, dy dx, I always do the same thing. I differentiate the y function. This is going to require a little bit of chain rule. It's going to be e to the t squared times 2t. And then I would differentiate the x function. The derivative of that x function is going to be 1 over 2 times the square root of t. Okay, and if you're algebraically satisfied with that, you could sort of leave that thing like that. You can also certainly do some algebra. I think that's 4 times t to the 3/2 times e to the t squared. And that's the end of the video, so I'll let you work out that algebraic simplification. Thanks for listening.